Okay, so in this video we're going to talk about the ideal gas law, and in particular we're going to start off talking about when to use which form of it. What I mean by that is, keep in mind the normal ideal gas law is just PV equals nRT, where R is the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. And you can use this to solve most of our equations. If you knew the pressure, the volume, and the temperature, you could find moles. If you knew moles, temperature, and volume, you could find pressure, so on and so forth. So if you have 3 and you're looking for the 4th, this is the form of the equation that you want to use. There's another form of this, which is what Avogadro's law, Charles' law, Boyle's law all sort of build off of, which is to say that since this is equal to a constant, if you were to rearrange that and just say PV over NT equals R, right, then under any set of conditions, PV over NT that satisfy the ideal gas conditions, it's always going to be equal to R. And therefore you can write this as a different statement. P1, V1, some initial set of concentrations over N1, T1 conditions, sorry, equals P2, V2 over N2, T2. Now this equation right here can be used at any point in time to calculate exactly what you need to figure out. So if we look at P1 V1 over N1 T1, if you needed to find just the relationship between pressure and volume, well, that means that moles and temperature are staying constant, so P1 V1 equals P2 V2. Or if you need to know between volume and temperature, volume 1 over T1 equals volume 2 over T2, and you just solve for whichever you're looking for. Okay, so these two different forms, this one right here is most useful, PV equals nRT, when you have a set of conditions and you're trying to find one of the variables. Okay, so I'm given a pressure, a volume, and a temperature, and I need to find moles. I solve for N. In the case of the lower one down here, this is useful when you're dealing with changes in conditions. You're given a pressure, you're given a volume, you're given some number of moles, some temperature, and you're trying to figure out from one to the other what the change is going to be. If I have pressure 1 and I change it to another pressure, what's the change to the volume? Okay, so that's when you use these two different forms. Alright, so let's take a look at how we can solve some of these problems. So the ideal gas law, what will the pressure be if you evaporate 15 grams of liquid nitrogen into a 2-liter vessel at 25 degrees Celsius? So again, the first thing to figure out is which form of this we're going to use. In this case, I'm given a mass, 15 grams. I'm given a liters, and I'm given degrees Celsius. So I have a temperature, I have a volume. I can use 15 grams. I know it's nitrogen gas, liquid nitrogen in this case becoming nitrogen gas. I can use that to calculate what the moles are going to be. And so what I'm really looking at is PV equals nRT, or to rearrange that in this case, P equals nRT over V. Okay, and that's what we're looking to solve here. So the way that we're going to approach this, first thing we need to do is we need to find those moles. So we're going to take our 15 grams of nitrogen gas, now it's going to be N2, molecular nitrogen, okay, and we're going to convert 1 mole into, it's 28.02 grams for 1 mole, and that's going to come out to 0.5353 moles of N2. So that's how many moles of nitrogen gas we're going to have in this vessel. Okay, so that gets plugged in right up here. Okay, R, 0.08206 liter atmospheres per mole Kelvin, we know that. Temperature I need to convert into Kelvin, so we're going to take 273 plus 25, and that will be 298 Kelvin. So that is going to go up for temperature. We know that we have a 2.00 liter vessel. So I simply take 0.5353 times 0.08206 times 298 divided by 2 for my volume there, and I get the pressure, which is equal to 6.55 atmospheres. Okay, so that's how you're going to solve this. The reason we wouldn't use the other one is in this case we're not changing any conditions. We're not starting with one volume, moving to another temperature, or anything like that. So we have to use PV equals nRT and just solve it for the one we're looking for. Okay, the next one we have is an ideal gas has a pressure of 3.5 atmospheres. If the size of its vessel is expanded to 3 times the initial volume and the temperature is doubled, what is the new pressure? So in this case we do have some condition changes, right? We have some initial volume that's being tripled. We have a temperature that's being doubled, so we need to start with the P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now in this case, notice our moles are not changing at all, so I'm actually just going to wipe the moles right out right now and arrive at the new equation that we're going to use. But in order to fill this in, we need to do some changing here. So first thing I'm going to do is I'm going to say, all right, well, I'm going to solve it for P2, right? P2 is equal to P1 V1 over T1. That's from the left side, and now T2 is going to come in here, and V2 is going to come in here. Now I notice that I have all these variables and I don't really know what to do with them. Well, the easiest thing is to get them in terms of each other. The problem gives us this information. So the size of the vessel is expanded to 3 times the initial volume. So I now know that V2 is equal to 3 V1. And the temperature is doubled. So I know that T2 is equal to 2 times T1, right? Doesn't really matter what T1 is right now. We're just looking at the initial concentration setup. So therefore, I'm going to sub these in. P2 is equal to P1 times, in this case I'm going to put the V's together, so V1 over 3V1, subbed in for V2, and T2 is actually 2T1, and that's going to go over T1. So if you look at that now, the V1 over V1 is just 1, can go away, T1 over T1 can go away, and what we're left with is P2 is equal to 2 over 3 times P1. And in this case, we know that that's 3.5 atmospheres, so 2/3 of that will be equal to 2.3 atmospheres. And that's how you solve one of these cases. You can do it with any sort of values, right? If you knew that V2 was actually 6 liters and V1 was 2 liters, you could just pump in the numbers 6 and 2. It's a little bit harder, so I showed how to do it with just the V1 and T1 and T2 method where you're not actually given a value, but anytime you're given a value, just put it right in and solve for the one you're looking for.